Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presence. The integration of OPTEX, optimization expert system, and GAMS, general algebraic modeling system. Case, high/power, enterprise-wide optimization system. Mathematical models. All models that integrate high/power have been developed using the OPTEX GAMS interface. The integration of the models is carried out automatically by OPTEX, and the generated programs coordinate their communication through the database, using monolithic models, or in RAM memory using large-scale parallel optimization. All high/power models can run in deterministic, or stochastic, version with user-definable uncertainty dimensions. Models can be solved using large-scale technologies, such as variations of Bender's theory, or Lagrangian relaxation, using parallel optimization to simultaneously solve all the problems in which the monolithic model is atomized. Finally, it is possible to introduce new models into high power as required. In the video, high power, enterprise-wide optimization system electricity and gas economic dispatch model. The interested party can review the entire implementation process of the electricity and gas economic dispatch model, which is the cornerstone of high power. High power, enterprise-wide optimization of companies in the electricity sector. Electricity system and wholesale market optimization models. Electricity system and wholesale market mathematical models. Traditionally, the optimization models in the electricity sector have been individual modeling with exogenous coordination between models, based on multi-stage stochastic programming, and using large-scale optimization methodologies. The differences provided by high power are integrated holistic modeling, scientific risk modeling, multidimensional uncertainty, parallel optimization, and autonomous real-time distributed optimization. The high-end core model corresponds to the integrated representation of electricity and gas supply chains. From the basic equations, variations of the model are generated, according to the techno-economic concepts that support a specific use case. The EANG equations represent the physical dispatch of an electricity-gas system, regardless of the market in which the system is located. The main variations of the dispatch model are related to the representation of the market where the EANG system operates. The process simulates an integrated system in which the two markets, gas and electricity, are balanced according to their operating hypotheses. With respect to consumers, models tend to assume an inelastic behavior of demand with respect to price. This hypothesis can be relaxed by modeling an objective function with variable demand, where the economy's social surplus is maximized. This is for any type of electricity and gas market. For the gas system, gas, supply and transport contracts can be incorporated, since this type of commercial instrument is commonly used in the gas market, and affects its operation. The main models on the electricity market are the EAD, Electricity Economic Dispatch, model optimizes the dispatch of generation infrastructure, minimizing the cost of operating the electricity system, which simulates a perfect electricity market. EAD is the core model of high power, as its equations/constraints are used in multiple specific models that the agent requires to address decision support needs. From EDD, 3 models of complementary dispatch are built: Economic Perfect Dispatch, Economic Regulated Dispatch, Nash-Carnot Equilibrium Dispatch, and Unit Commitment. The first 3 models are oriented to planning and the fourth to real-time programming. 3 types of connectivity of the generation system and the transmission power grid are considered. Ideal single node, ideal dispatch ignoring the transmission system. Electric transmission network connectivity based on the detailed connectivity of the electricity transmission system using bars and circuits. Operative areas connectivity, when the user does not have, or does not want to use, the detailed configuration of the electricity transmission grid. It is possible to use the connectivity based on operational area //app. Blaster online. com/speech low/changelogs including limits on the transfers between areas. Interconnection electricity, gas integrates electricity network with natural gas network. Interconnection electricity, water can be fully detailed, including travel times between nodes and transport restrictions in water resource conduction channels. Economic regulated dispatch, delivery of plants that minimizes the cost of operation of the interconnected system and includes representatives aspects of the regulatory of the electricity market being simulated. It does not correspond to a model of economic equilibrium, however, it is an easy and fast way to represent regulatory considerations based on optimization models. As a starting point, the traditional economic dispatch model, EDD, is used. The extended model is equivalent to a minimum cost dispatch model, considering the normal operating costs plus the costs derived from regulation. The new model has two types of variables and restrictions, those of physical dispatch, (YANG), and those derived from the regulated market. This model assumes perfect competition between generators. The difference is that they are informed, rational generators, which include as part of the analysis the costs, or benefits, that derive from regulation. The non-inclusion of regulated costs implies an erroneous analysis, which should generate biases in the user's decisions. The high ERD model can be used too. Agent decision-making, same as with the simple economic dispatch model, but using a better approach, and analysis of the impacts of regulatory proposals, valid for any of the authorities and market agents. Ignoring that the regulations affect the firm seems to be a naive position. Nash-Carnot equilibrium, dispatch of plants oriented to the simulation of competitive electricity markets with agents that can influence their decisions on transactions occurring in the market. It can be used to, among others, project the dispatch of a competitive market, and study the exercise of dominant power of agents. The best way to visualize the NCD model is to break it down into its parts, each of which is a mathematical problem. The first model represents inelastic demand, or not, that accepts, or does not accept, the offers of generators. This model represents society. Normally this function is performed by the ISO, interconnected system operator, which assumes the function of implementing the optimization process, through a spot market model with physical and commercial restrictions. Depending on the regulation, the modeler can define prices, or quantities, or prices and quantities. In the second level, there are generators that make their offers, which are sent to the ISO, which decides which ones to accept, which to reject, and defines the spot price. Market equilibrium is achieved in an iterative process. This is a form of market, common in competitive markets, based on offers from agents. It must be considered that equilibrium, the optimal for society, is achieved in an iterative process, and never in a process of a single pass. If it becomes so, it would be a coincidence. Solution methods can be Lagrangian or Bender's coordination, and mathematical programming with equilibrium constraints, MPEC. In competitive electricity markets, generating agents form a Stackelberg-type oligopoly, in which there is a small group of dominant agents, price makers, and the rest are dominated agents, price takers. The dominant agents have the strength to define prices, and the dominated agents must accept them. A three-tier model can determine break-even points for this type of market. The effect of the difference in the results of the two models, economic dispatch and competitive dispatch, is seen below. The image, take from the conference bid-based dispatch in large-scale hydro systems, given by Luis Barroso, presents the production of hydropower in a competitive market, in which agents take strategic positions. In this case, hydropower will be lower than in markets dispatched by traditional models. On the other hand, if spot prices are analyzed, the strategic position of the generating agents will produce higher spot prices than the minimum cost dispatch models. Obviously, if an agent uses minimum cost dispatch models to estimate their income, price by quantity, it is possible that the financial accounts do not add up. Unit commitment associated with operational scheduling decisions related to dispatch plants by the hour, or by more detailed periods, respecting all nonlinear and discrete restrictions. Scheduling power plants is the final step in the planning process, for a region or a company. To ensure long-term optimality, the planning horizon should cover the seasonal cycle of climate processes. There are two alternatives to control the optimization process. First, a monolithic model that integrates two problems. Medium-term planning, economic dispatch of electricity, ED, in the order of months, and programming of electrical assets, unit commitment, UC, in the order of hours. Based on OPTEX's vision, building an integrated monolithic model is a matter of cutting and pasting equations, regardless of the type of dispatch model that is right for the market. The solution of the monolithic model can be realized with large-scale optimization methodologies. To this end, the planning horizon is divided into two periods. 1 to TCP, modeled as a UC problem, and TCP plus 1 to T, modeled as an EAD problem, or as a variation of EAD. In this case, the integration is carried out by means of the system state variables, the inventories at the end of the TCP period, with the initial inventories of the DP model. This involves introducing equality constraints to enforce the coupling. This model unites short-term scheduling with medium-term planning. The integrated model can be solved using large-scale optimization techniques, such as Bender's partition and Lagrangian relaxation. This approach decreases solution time and memory requirements. The traditional way of approaching the problem is to coordinate the two models, solving each of them independently, offline, in such a way that the EAD model establishes the boundary conditions of the UC model, which can be interpreted as the optimal operating goals. This approach may not have a feasible solution in UC, due to differences and/or approximations could lead to the non-viability of the set of goals set by the EAD for UC. There are two alternatives to carry out coordination. The chaining, or coordination, of models does not guarantee optimality. There are always at least two alternatives to concatenate two models. By the prices, or dual variables, that is, the value of water, or in general the value of resources. Coordination through economic variables, dual variables or prices. To this end, the opportunity value of inventories is established at the end of the TCP period. In this case, it corresponds to the value of the water. The application of this approach must be careful, since the boundary conditions must represent the variation of intra-period prices, but, in general, it is only a matter of considering a sample of the value of water, only one point, at the beginning or at the end of the planning horizon. This can lead to water value profiles, as a function of the reservoir level, which are far from the profile estimated by the EAD model, which is not known to UC. Another problem lies in the fact that the value of water is assumed to be constant throughout the UC planning period, which is not necessarily true. This approach always gives feasible solutions, but they can be far from optimal, due to the distortion of the dynamic price profile. The other possibility is, by the quantities, or primal variables, that is, the use of water, or in general the use of resources. To this end, the quantities of resources to be used and the quantities to be produced of industrial products during the period of operation from first period to the period TCP are established. Inventory levels to be achieved at the end of the TCP period are also established. This approach does not distort the dynamic price profile, but it may not have a feasible solution, due to the differences between the two models, as the planning model is always relaxed with respect to the scheduling model. Non-feasibility can be managed by soft constraints, which introduce penalized slack in the target function, to ensure that the final schedule is close to the optimal target set by the planning model. Quantity coordination is done through goals and resource inventories at the end of the UC model planning horizon. These objectives imply that the total use of resources in UC is pre-established, which may or may not be achieved. The two methods do not have to give the same results. Cyclical coordination can produce the optimal solution, or correct unfeasible solutions. High power optimization models for agents' decisions. Four models are considered fundamental to support the strategic, tactical and operational decisions of the industrial agents. The diagram presents the design of the integrated use of mathematical models to support the decision-making of a generating agent. In the same way, all models make up the artificial hypothalamus of the wholesale market of the electricity sector. Electricity supply chain design and risk management. Associated with strategic planning, long-term decisions related to design supply chain, in relation to capacity of reservoir, transfers, power plants and other assets of an electrical system. It includes risk management and financial planning. Electricity dispatch and financial analysis. Integration dispatch models with ALM, assets liabilities management, financial models, including risk management, to perform analysis of the financial impact of decisions. The main applications of high-power ALM are the valuation of income and expenses of investment projects, energy installations, and valuation of companies. Integrated optimization of investments by global energy companies, taking as a reference the regulatory laws of the different regions or countries. The financial modeling results individualize the operating income and expenses, and can include all types of legal accounts. Energy trading and risk management. Optimal decisions related to trade energy and coverage of financial risks based on standardized or bilateral contracts. It corresponds to a set of mathematical models aimed at supporting the decisions of the different agents involved in energy trading in I. Long-term market, 2. Spot market, and 3. Secondary markets. The result of a risk analysis is the definition of Pareto curves of financial risk versus expected revenues/costs, based on which the decision maker must define the risk position he wishes to assume, varying between risk-prone and risk-averse. Maintenance optimization is oriented policy making preventive maintenance of multiple central generation plants and others electrical assets. It can be applied to all assets in a regional or national grid. High-power MAN can be implemented following the principles of PHM, prognostics health management, for industrial asset maintenance, integrating specific models of predictive analytics for asset components and prescriptive analytics to optimize the integrated operation of the asset network. High power has been used by ISO, in Peru, and market supervisors, in Colombia, for planning and decision-making purposes. The power of enterprise artificial brains. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. This allows us to talk about autonomous real-time distributed optimization. Algorithms swarm, the actual state of artificial intelligence using artificial brains. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.